Makes it very easy to remember, very easy to use in organic chemistry, which is the most important part. Is it useful for you? When it comes to pKa values and acidity, I tend to take a very pragmatic approach. I don't particularly care if you memorize specific pKa values for specific molecules. Instead, I like to group molecules into 9 classes of acids. These classes of acids, you need to know the 9 pKa values for the 9 classes of acids. The other way I like to be pragmatic about pKa's and acidity is within a class of acids, it doesn't really matter what the specific pKa value is. For example, when you think of the class of alcohols, your textbook probably says something like the pKa of alcohols is somewhere between 15 and 18. Does it matter if it's 15? Does it matter if it's 18? I guess in certain specific circumstances, but we're not there yet. We're just learning organic chemistry. So let's just give one value for all alcohols. As we get more sophisticated, we can figure out which alcohols are more acidic or less acidic than which other alcohols, but even then it doesn't matter what the specific pKa value is. As long as I know it's near 15, it's more acidic than this other alcohol, that's really all that matters. Very pragmatic approach. So I'm going to call it pKa on the 5s, just like your local radio station. I can map the 9 pKa values to a multiple of 5 on this pKa continuum. Makes it very easy to remember, very easy to use in organic chemistry, which is the most important part. Is it useful for you to help you figure out how to do organic chemistry? So let's get started. The first class of acids that I want you to know is the mineral acids. The mineral acids we can all group at about a pKa of about -5 or so. The mineral acids are your Gen Chem acids. These are the ones you learned in Gen Chem. Sulfuric acid, hydrochloric acid, phosphoric acid, nitric acid. These are your Gen Chem mineral acids. They're the strongest class of acids, and we can give them a pKa of about -5. Do any of these actually have a pKa of -5? Probably not. But what's interesting, if you go look up the pKa value of sulfuric acid in a couple of different textbooks, a couple of different websites, I found like 4 or 5 different numbers for the pKa value of sulfuric acid. So if we can't all agree on the pKa of sulfuric acid, why can't we just call all mineral acids -5? Very pragmatic, very useful. The next pKa class then to know is the protonated oxygen. These have a pKa of around 0. Actually around 0? I don't know, probably close enough. Protonated oxygens are any oxygen that has 3 bonds and a positive charge. Protonated oxygen. So a protonated alcohol, a protonated carbonyl, a protonated ether, any protonated oxygen will have a pKa value of around 0. The most prototypical in this class is H3O+. Does it have an actual pKa value of 0? No. What is its actual pKa value? I could go look it up, but I don't actually know. It's close enough to 0, but that's fine. Very pragmatic, very practical. The next class of acids is carboxylic acids. Carboxylic acids have a pKa of around 5. This one's actually pretty close to true. Most carboxylic acids really do have a pKa of around 5. Doesn't matter if the carboxylic acid is attached to a benzene ring. Doesn't matter if it's attached to a carbon chain. Acetic acid is the most prototypical example of a carboxylic acid. Around 5 is good enough. Fourth class of acid would be the protonated nitrogen. These are nitrogen with 4 bonds, positive charge. Protonated nitrogen. Ammonium is the most prototypical example of a protonated nitrogen, but any nitrogen with 4 bonds, positive charge is going to have a pKa of around 10 or so, give or take. The next class of alcohols is alcohols. Alcohols have a pKa of around 15 or so, give or take. Alcohols are molecules with a single OH bond. And alcohols have a pKa of around 15. The most prototypical example of this class is water. Water has a pKa of around 15.7 to be specific, but I don't really care. Close to 15, close enough. Even if the alcohol has 3 fluorine groups, which are electron withdrawing, got a whole video linked below about how we can modulate the electron density around a molecule, and a different video linked below about how we can rank acids according to their acidity. But it's still around 15. It's going to be a little bit more acidic than regular ethanol, but it's going to be around 15. That's close enough, good enough. The next class in our list is carbonyl alpha protons. Carbonyl alpha protons, we need to be very specific. They are the hydrogen on a carbon next to a carbonyl. Carbonyl alpha protons. Carbonyl alpha protons have a pKa of around 20. It's really around 20 to 25, depending on what kind of carbonyl it's next to, but it's okay. It doesn't matter. Around 20 is going to be good enough for carbonyl alpha protons. One word of warning. We have some aldehydes drawn up here. Notice those aldehydes are not folded in red as acidic protons. The H of an aldehyde is not an acidic proton, friends. Don't try and deprotonate it. The alpha proton is the hydrogen on the carbon next to the carbonyl. After carbonyl alpha protons is alkynes. Alkynes have a pKa of around 25. The hydrogen on the end of a terminal alkyne has a pKa of around 25 or so. After alkynes is regular amines. So we had protonated amines earlier. This is regular amines. Regular amines have a pKa of around 35, 37. The different textbooks, again, will say different things, but again, it doesn't really matter. As long as you know the pKa is around 35, that's plenty good enough to do what you need to do with the reaction that you're trying to do. And our last class that we need to know is regular boring alkanes. I've got methane drawn out with its hydrogens. I didn't bother drawing the hydrogens in the other ones because there's literally dozens of hydrogens that I would have had to have drawn up there. Any hydrogen attached to a regular old boring regular alkane is going to have a pKa of around 15. These are the 9 classes of acids from most acidic to least acidic. We can use this if I can look at a molecule and figure out which class of acid it is. That's going to help me know what to do in the reaction. That's going to help me know if an acid-base reaction is favorable. That's going to help me know if I can protonate this molecule with this acid. It's going to help me to know if I can turn a leaving group into a better leaving group. All these things we're going to do in chemistry. If we can narrow it down to one of these 9 classes of acids, that's really as precise as you need to be at this point in your chemistry career.
Thanks for watching. The best way you can support this channel is to let your friends know about these videos, especially ones who go to different schools. Help spread the word around the country. As always, don't forget to like and subscribe.